All right, section 2E is on inverse functions, and these are what we would call the undo buttons of math, and you already know a little bit about these without even realizing it. You use these when you solve equations. So if you're solving the equation 5x equals 10, you would divide both sides of the equation by 5, okay? Because division by 5 is how you undo multiplication by 5. Likewise, if you were solving x cubed equals to 8, you would take the cube root of both sides. You would take cube root, because a cube and a cube root, they're kind of each other's undo buttons. They cancel each other out. And that's the point of an inverse function. It undoes whatever the original function does. All right, so let's say we wrote our multiplying by 5 function, 5 times x, then we would say that the inverse function is the function that divides everything by 5. So we would write it this way. Okay, so that's the function that does the opposite of what f of x does. Now that notation that I use, it looks like I put a little -1 exponent there. We read this as f inverse of x. That -1 is not an exponent. It's one of the most unfortunate bits of notation we have in mathematics. So this is not an exponent. There is such a thing as a negative exponent, and it does good things for us, but this is not an exponent. So I wish we had picked something like a 4-leaf clover symbol to put up there that says, hey, we're doing the inverse now, but we're kind of stuck with this -1. Just keep it in your mind that it's not an exponent. All right, so with this notation, we could also say, if f of x is the cubing function, then f inverse of x is the function that takes the cube root. All right, so inverse functions are the functions that undo their partner functions. There's another way to think about them. So let's think about, if I take f of x here, if I find f of 2, let's see, 2 cubed is equal to 8. And that means that if I plug 8 into the cube root function, the cube root of 8 is 2. All right, so inverse functions also have this habit of swapping inputs and outputs, right? So what was the x for the original function is the y for the inverse function, and what was the y coordinate for the f of x function is the input or the x of the inverse function. They swap inputs and outputs. And this is actually how we define inverse functions. The inverse of f of x, denoted with that terrible notation, is defined by this. F inverse of x equals y means f of y is equal to x. They swap inputs and outputs. So input for the inverse is the output for the original function. Output for the inverse is the input for the original function. All right, so let's get some practice with this, and also notice something important about graphing inverse functions. All right, so I have this graph posted on Moodle if you want to take a look while we do this. So I've got this very odd f of x function. Let me actually label that. This is f of x. All right, and we're going to try to graph f inverse of x just by looking at the points on f of x. All right, so let's start over there on the left. We have this point over here that's -3, -1. All right, so we know that inverse functions swap inputs and outputs. They swap x and y values. All right, so if I swap those x and y values, I'm going to get the point -1, -3. That's going to be down -1, -3 down there. Okay, so that's going to be a point that is on the graph of f inverse of x. All right, so I'm going to go, let's see, what's another, let's pick that end point on the right. We have the point 2, 3. Right, so that means that f inverse is going to have the point 3, 2. So 3 in the x direction, 2 in the y direction. It's going to be there. Let's pick a couple more points to plot. F of x has the point 1, 2 up here. So we'll swap those and make it 2, 1. So 2, 1 puts me right there. I'm kind of just picking the corners on this graph. The last corner point that I find for f of x would be this 0, 0 point. And when I swap that point, 0, 0, goes to 0, 0, that point actually is going to be shared by the f inverse function. And if we take a little leap and assume that because f of x is a connect the dots kind of graph, then so will f inverse be, which ends up being a decent assumption, we're going to get a graph that looks like this. And even if you don't have good words to describe it, you can see what the relationship is between these two graphs. They're kind of a reflection. They're not the reflections that we did in transformations. It's not a vertical reflection or horizontal reflection. It's actually a reflection over the line y equals x. And I'm going to draw that as a dotted line here. Y equals x is that angle, that 45-degree angle line. Okay. And it's the line that goes through all the points that have similar x and y coordinates, or the same x and y coordinates, the point 1 comma 1, 2 comma 2, 3 comma 3. And those are all the points that don't get changed when we go from the function to the inverse, right? 0 comma 0, the x and y coordinates are the same. So when we flip them, they don't go anywhere. All right, so that y equals x red dotted line is kind of like the hinge that we're going to grab, or the axis that we're going to grab to rotate and figure out what the graph of f inverse looks like. Okay, so we're going to write this down as a rule. The graph of f inverse of x is the graph of f of x reflected over the line y equals x. And this fact is going to tell us something really important about inverse functions. All right, so here I've got a function f of x, looks like a transformation of x squared. And we're going to try to picture what it would look like if we swapped all the x and y coordinates and found its inverse. All right, so I've got that line y equals x. So you're going to imagine what would happen if you folded the paper along that dotted line and you reflected f of x over that dotted line. All right, so one point will be easy for us to kind of get a concrete hold on. This is the point -3 comma 2. So let's swap those x and y coordinates to -3. So the inverse would land down here. And what would end up happening, it would look something like this. Okay, so if you can imagine folding the paper along that red dotted line, the black graph would fall right on top of the blue graph. Okay, so what's the problem with my inverse function? The problem is that that function is not actually a function. Remember, how do we tell if things are functions? We see if they pass the vertical line test. Okay, so this fails the vertical line test. So this is not a function. Okay, so we can't even use that notation. It's not a function, so it can't be an inverse function. All right, so what is a vertical line problem for the blue graph is a horizontal line problem for the black graph. Okay, so we're going to have to say that if the original function doesn't pass the horizontal line test, then there's not going to be an inverse that's going to pass the vertical line test. Okay, so in order for a function to have an inverse, so in order for f inverse of x to exist, f of x must pass the horizontal line test. All right, and you'll see in your book that they call a function that passes the horizontal line test a one-to-one function. All right, so a function that passes the horizontal line test is called one-to-one. All right, so a function has to be one-to-one in order for its inverse to exist. It turns out that we are so desperate for inverse functions that we will actually chop our graphs up to force them to pass the horizontal line test so that we can find their inverses, which is what I'm going to show you in part when we meet together in class.